Okay, I'm presenting this work done in collaboration with Garthwells, whom I think you all know. I'm from University of Bologna, and Garth is from the Department of Engineering from the University of Cambridge. I'm presenting an example, an application of Dolphin. I tried to implement a phase field model in Dolphin, and I will show you how we did that. First of all, the motivation for what we did. We started from a point of view very applicative. We wanted to predict the microstructure resulting from a process, a technological process which is called heat treatment, to in general predict in a better way the mechanical properties, and also to give some tools for the setup of the technological treatment. But pretty soon we realized that the way in which this thing was treated in literature, I'm referring to technical literature, wasn't really good. So we decided to switch to another point of view, which is basically a thermodynamical point of view. And these are some microstructures as they appear from microscopical observations. And we first tried to implement our model in a handwritten code in MATLAB, but once again we realized it wasn't the right way, so we knocked at Garth's door and we asked him for help, and introduced us to Dolphin, which is actually pretty powerful. I hope I'll be able to show the advantages we took from using and implementing our model in Dolphin. We got three different equations basically. One is a diffusion equation, which is called the Canillard equation. We have then the balance of linear momentum equation and the balance of energy equation. Let's start from the Canillard equation. It's basically, this is the local form of the equation. It's basically a balance of mass of carbon, because one transition is driven by the amount of carbon moving from one part of the domain to another one. And these are the constitutive relation which flows from thermodynamical considerations. This is how the flux is expressed. This is the chemical potential, which is a functional derivative of the free energy, the Helmholtz free energy. Those are the boundary conditions. This is a non-local boundary condition. This is our initial condition. As you can see, it's a fourth order operator, 2, 3, and 4, and we decided to split in two equations, both of second order, both containing a second order operator. This is the first one, this is the second one, and this is the weak formulation. We obtained discretizing in time with a theta method scheme. Basically, this is the evaluation of the time derivative of the C, which is the concentration, the mass fraction of carbon, and this is the term evaluated at an intermediate point weighted by this parameter, which is called theta here. This is the second equation. In this way we could recover the boundary condition, both boundary conditions. This is how the code looks like, and you can see that here the parameters are set for having a trapezoidal rule, and this is a definition of a function. We need to have a chemomechanical coupling, and this is the expression for the chemical potential, and after that we write the weak formulations for the linear form, and for the bilinear form we recently have implemented the automatic derivation. I'll show later what's the advantage of doing that. We have then the balance of linear momentum equation in its local form looks like that, and those are the constitutive equations, once again flowing from thermodynamical considerations. Particular attention should be given to the gradient part of the stress tensor, which looks like that. This is C2, which is somewhat a function of the strain tensor and thus of the derivative of the displacement on the gradient of the displacement. And these are the boundary conditions. This is especially a non-local boundary condition, and those are the initial conditions. The equation is contains a fourth order operator once again, 2, 3, and 4, and this is the weak form. The regular part of the stress tensor can be treated as usual, but we decided to give a special treatment to the gradient part of the stress tensor. We implemented it with a discontinuous Galerkin approach, and this is how it looks like. In this way, we were able to recover the non-local boundary condition. And this is what we used for the time derivatives. We have a so-called generalized alpha method in which we weight with a different weight the derivative for the inertial term and the derivative for the stress term. Let me notice that as the stress tensor is nonlinear, we should this is the correct way to evaluate the stress tensor at an intermediate point. We take the displacement at n plus 1 and the displacement, there's a typo, sorry, at n, and not the stress tensor evaluated at n plus 1 and at n. This is how the code looks like, and we got some definitions here for everything we need. This is for the acceleration, this is for the velocity, this for the displacement. We define a function, as we saw before, which is accounting for some strain quantities. And after that, we define the stress tensor. This is the regular part, and this is the gradient part. Then we set up the linear forms, we sum them, and once again we perform an automatic derivation. The last equation is the balance of energy equation. This is its local form. It's not the usual heat equation, but it's called a complete heat equation, in which we can see thermomechanical coupling, thermochemical coupling, which is here and here, and this is the classical Fourier rules. These are the constitutive relations. I showed them before, so nothing new. And these are the boundary conditions and the initial condition.